Hi, so this section is about something called elementary matrices, and we're going to see a way of calculating the inverse of any matrix. So we saw in the previous section how to do it for a 2 by 2 matrix, but what if I have a 3 by 3 matrix? We're going to see a way that's based on Gaussian elimination to calculate the inverse. But first we start with elementary matrices. Those are related to actually row operations. So remember there are three of them. So we can multiply a row by a non-zero constant. We can interchange two rows, or we can add a multiple of a row to another row. So our goal here is to perform these row operations by doing a matrix multiplication. Okay. So let's start with that. So we'll work with a 3 by 3 matrix, okay, and we'll perform row operations on it. Well, you'll see that what I'm doing here applies easily to any type of matrix independently of its dimension. So I'm going to say that I have a 3 by 3 matrix, A, B, C, D, E, F, G, H, I. Okay, and let's say I want to perform, say we want to do, replace row 1 by row 1 minus 3 row 3. So I'm doing the third type of row operations listed up there. Okay, and what I'd like to do is I'd like to have a matrix E, so that when I multiply E by A, I will get the matrix where this operation has been performed. So what is that matrix? Well, I want to replace row 1 by, so I want to replace A by A minus 3 G's. B, I want to replace it by B minus 3H, and C by C minus 3I. The other rows remain unchanged. So the question is, what matrix will allow me to do this? And of course it has to work independently of what the entries of A are. Okay, so I could try to figure out, like, just by trial and error, what my matrix E should be. In many videos that talk about elementary matrices, they do this. Maybe I want to show you a way that I find more straightforward. So let's say, so here A could be anything, right? So what if A is the identity matrix? Okay, if A is the identity matrix, well, remember the identity matrix here would be the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. So what if that matrix E, which when it multiplies any matrix, performs the row operation where row 1 is replaced by row 1 minus 3 row 3. If it's applied to I, well, the same happens to I will be changed. So the first row will be changed, and I'm going to apply this row operation to I, because that's what multiplying by E is doing. So if I take the, let me just turn that off. Okay, so if I change the first row of the identity matrix, well, I'll do 1 minus 3 times 0. So that's just 1 here. And then 0 minus 3 times 0, so 0 here. And this entry will be 0 minus 3 times 1, so minus 3. And the other two rows are unchanged. Okay, so that's what it does to I. But hang on. Remember that if I multiply any matrix by I, it stays unchanged. So actually, this guy here, EI, that's just E. So actually, I get for free what the matrix E is. It's just this matrix. Isn't that pretty cool? If you don't trust me, let's check again. If I do E times A, okay, you multiply by A, that's D, E, F, G, H, I. If you multiply these two together, let's check that we get back this matrix here. Let's see if it works. Okay, so actually, if I multiply by the first row, every column of A, what happens? So 1 times A minus 3, well, plus 0 times D minus 3 times G, well, that's A minus 3G. And after that, it's B minus 3H and C minus 3I. And when I multiply the second row of E by every column of A, actually, it's not too hard to see that I'm just going to get back the second row. And same goes for the components in the third row. They're obtained by multiplying 0, 0, 1 by all the columns of A. And yes, we do get the exact same matrix. Okay? So that's why you'll find the following definition in the book. So we have that an n by n matrix is called an elementary matrix if it can be obtained from In by performing a single elementary row operation. So for example, in the computation we did before, we get the matrix E by performing the row operation row 1 minus 3 row 3 on the matrix I3. So here's an example. So we want to write a 3 by 3 elementary matrix which performs each of the given row operations. So I've recopied matrix I because we're going to essentially find those elementary matrices by applying those row operations to I. So it's very easy, right? So we could call maybe the first one E1. E1, all I have to do is change row 2. So row 2 is changing, but the other two rows are not. And after that, I perform this row operation on row 2. So I get 0 minus 2 row 1, this, and this. Here we go. That's the first elementary row matrix. Elementary matrix. B is very simple again. I'm going to interchange row 2 and row 3. So row 1 stays unchanged. Oop. And I just changed the last 2 rows. And that's E2. And E3 is multiplying the second row by a half. That. And that's it. Next question is, find the inverse of the previous matrices. And you'll say, hey, hang on, we haven't seen how to find the inverse of a 3 by 3. But here there's a trick, because remember, the elementary matrix is related always to a row operations, and those row operations are invertible. I can always perform another row operations to go back to the state where I was initially. So if I want to cancel the row operation where row 2 is changed by subtracting 2 times row 1, what do I need to do? I need to add back again row 2 times row 1. So the inverse of E1 is the elementary matrix that performs that row operation. So what is that? That's 1, 0, 0, 2, 1, 0, 0, 0, 1. And if you don't trust me, you can always check, right? How do you check? If you're right, E1 times its inverse, if it's the right inverse, of course, it should give you I. So if you do 1 minus 2, 0, 0, 1, 0. Okay, so that's E1. You multiply by the inverse that I wrote above. Like if it's the right inverse, I should get back the identity. So if I multiply this this row by every column here, of course it's not going to change this guy. First row, if I do minus 2 times 1 plus 2 times 2, that's 0. Minus 2 times 0 plus 1 times 1, 1. 0 here again. That's not too hard to see that, yes, I get the identity. Okay, so I'm not going to do this every single time. Okay, but you see that it works. If I'm not unsure, I can always check it. E2 inverse, what is that? Well, that's the opposite of interchanging, well, I've interchanged row 2 with row 3, so what do I need to go back to my initial state? I need to change them again. So in fact here, this row operation is its own inverse, so that means that E2 is its own inverse. So that's kind of nice. So we see that if we have one of these elementary matrices that interchange two rows, it's always going to be its own inverse. And for C, I need to multiply row 2 by 2, so we get this very easily. So that explains the following theorem, which says that every elementary matrix is invertible and the inverse is also an elementary matrix. And again, that's just because the inverse of a row operation is another row operation. That's it.